Okay.
Okay, you've seen my screen now, right?
Yes.
Yes.
Yeah, okay.
Yes, Professor.
Yeah. So the project presented by Dr. Ahmed has been more advanced later to bring it into more practical application. So now we are talking about a real unit, a real thermal energy storage unit based on phase change material fabricated with metal foam. So let's start with the motivation. Dr. Adel, I think, highlighted those aspects, and no need to reconsider them. So the thermal energy storage basically classified according to the technology adopted into three types. The sensible heat thermal energy storage, which is made by sense of temperature rise or decrease, while the latent heat thermal energy storage is it involves some of sensible heat thermal energy storage before and after the melting, but during the melting time, the unit is gathering heat in terms of latent heat of melting, or they call it latent heat of or solidification. It is the same. So this method in particular is quite interesting because it offers high energy density, and there is an extensive range of phase change materials with a wide range of melting temperature. So for example, we've got phase change materials with melting temperature starting from 5 degrees centigrade up to 500 degrees centigrade or even more. So according to the application you're tackling, you can select from this diversity, okay, and implement it into your system. The other advantage is quite it's chemically stable, okay. The one disadvantage regarding this way of thermal energy storage is the poor thermal conductivity that most PCMs exhibit. Okay, so this thermal conductivity significantly delays the charging and discharging rates, and hence, let's say, make a problem for the overall performance. That's why there are, by the way, there are many ways to overcome these problems, mainly by improving the overall thermal conductivity of, yeah, but I'm talking now about something else, please. The idea here is to improve the overall thermal conductivity, either by direct or indirect ways. There are two procedures. The indirect ways, okay, by using some highly conductive inserts like fins, extension metal surfaces, or maybe heat pipes, and the other procedure is using the metal foam. The indirect, the direct procedures, on the other hand, is based on increasing the thermal conductivity of the PCM itself, either by using some nano powders, or using what they called some nano matrix. Anyway, so we are our focus in this project is on using the metal foam. The metal foam, as you see, is a matrix of interconnected pores, allow the fluid to flow inside. They are made of metal, so they've already have the feature of high thermal conductance. So this allow us to transport heat efficiently and in the meantime, reduce the pressure drop penalty. Those aspects have been already covered by Dr. Adesoni. No need to uh, waste time on them. So the physical model in this project is a real unit. It's formed of bundled tubes, of bundled tubes arranged in a staggered way. Okay. So those tubes, we've only uh, simulated a single row of those tubes. So the heat transfer fluid, which is water in the system, is coming from the bottom of the unit and flowing upward. While flowing upward, the heating water, okay, flow through the voids between those tubes and get accelerated. With this acceleration, heat transfer rate is significantly promoted. Thus, on the side of the heat transfer fluid. What about the PCM side? The PCM side, which is inside those tubes, is formed of two different materials: the PCM and the copper form. Okay, that is saturated, fabricated with. So in this system, we've got four different, four physically different regions, which are the heating fluid, which is water, the tube walls, which are made of copper. Inside the tubes, we found the PCM and another identical region sharing the tube area, which is the metal form. So what we've used as a phase change material is the paraffin with these thermophysical properties. The melting temperature is between 54 to 64 degrees centigrade, where the mushy region take place. Okay, look at here to the thermal conductivity is relatively low compared to the thermal conductivity of the copper. So again, the physical model, the mathematical formulation is based on the continuity equation and the momentum equation in conjunction with uh, energy equations. So let me, okay. There is something interesting here. As the thermal conductivity of the copper is much more higher than the thermal conductivity of paraffin. In porous media solvers, you can't deal with such phenomena as and assume that there is a local thermal equilibrium. There is a local thermal non-equilibrium exists. That means at a certain point within the tube, there is no thermal balance between the metal foam particle and the PCM particle adjacent to it. So there is what we call it interstitial heat exchange. The fluid get some heat from the solid. Look, this, okay. So this is the energy equation for the molten PCM. So there is an extra heat absorbed by the PCM, but that heat is already conducted from the tube walls through the solid matrix. So the solid matrix with temperature T sub S is losing its heat content to the liquid. Okay, that's why we had to implement this model. The last energy equation is for the thermal conductance through the tube walls. Sorry. Okay, Those are the permeability, initial coefficient, thermal effective thermal conductivity, and the other parameters required to track the thermal energy. This is what we call the liquid volume fraction. So you see, we've got two melting temperature for any PCM. The first one, which is the lower temperature, is called the solidus temperature, and the higher temperature, the higher key temperature, it is called the liquidus temperature. Between them, there is a mushy region. Okay, so lower than the liquidus temperature, all the PCM is in solid phase, so the volume fraction is zero. Higher than the lower than the solidus temperature, the liquid fraction is zero, while higher than the uh, liquidus temperature, the liquid fraction is 1. Okay, moving on, the initial conditions at the beginning, as it is a charging process, the components inside the PCM are all at the beginning at low temperature, which is 22 degrees centigrade, while the fluid outside the tubes, which is the heating water, which is supposed to charge the tubes, are at relatively much higher temperature at 80 degrees centigrade. For the grid generation, we've selected only a half of the row selected because we've got symmetry planes on both sides, so no need to double down the computational domain. Okay, this mesh has been generated using the pointwise meshing software, and attention has been paid at the interfaces between the the physically different regions. So this is the water, this is the conducting surface, which are the tube walls, and those the PCM metal foam composite. And as you see, that mesh has been refined close to the areas where some rapid changes might take place. So also a grid dependency, a pre-simulation has been done to check the grid dependency in terms of the local evaluation of the liquid volume fraction at the middle tube, tube number 6, at 3 different locations, and for four different grid sizes. As we see, the difference between the grid, the third grid and the fourth grid becomes quite marginal, so no need to go for the larger size, and the third one, which is 85 632 cell, is quite sufficient for the current simulation. Regarding the discretization method, it is the finite volume with a spatial discretization using the linear upwind differencing scheme for momentum and energy, and plus the Presto for pressure. For the temporal discretization, we've selected the second order implicit, and simple algorithm has been employed for pressure velocity coupling. Finally, ancillary fluid has been utilized to run the current simulation with time step equal to 0.5 seconds. This time step size has been decided based on pre-simulation to check the time step size required for the accurate simulations. As we see that between time step 0.5 and 0.25, the changes vanish. So we've selected the third time step, which is 0.5 second. for the validation, we've done some re-simulation, also replicate some experimental data, and you see the development. This is the liquid diffraction, the development with time. Those in the row below are the volume fraction development, and the upper row is our simulation. So there is no big difference. And in regards of the temporal, the development of the foam and PCM temperature at certain points, they are also compared and gave some satisfactory agreement. Now let's get to the results. First of all, as Dr. Adel demonstrated before, we've compared the metal foam composite with the pure paraffin. So this is the pure paraffin at the first minute. The one on the right is the liquid diffraction, and on the left, the PC paraffin temperature. So we see now how the flow developed, and the
Dr. Ahmed is
thermal...
not showing. Dr. Ahmed, you have to share the screen, please.
Really?
Sir, it's visible, sir.
Is visible.
Can you
Yes,
see
sir.
it
Pure
now?
paraffin. Yeah, I can see. It's visible.
I'll reshare it now. Maybe there is a problem with it, but
Yeah, it's visible. I can see it.
what about now?
Dr. Ahmed, reshare it.
Yes, okay,
again.
right.
Yeah,
right.
I reshared.
Yeah, it's visible.
Yeah, you can
Okay.
exit and reshare it if there is a problem for sir. Yeah.
Has been solved now?
It has,
Problem?
Dr. Ahmed.
Okay. So if we see here, that's let's go back few time steps. So these are the distribution for the temperature field and liquid diffraction after 1 minute. This is for the pure paraffin. Okay. After 3 minutes, we see how the tubes being thermally charged, and there is a thin layer of liquid start to start to generate, start to evolve. Going further, we see how the upper side of the tubes start to be melted completely, while the solid mass start to drop down due to gravity. Okay, I think it's more demonstrated here. This is after 19 minutes, and the melting process starts until it's completed after around 31 minutes. This is for porosity 0.97 and pore density 25. So regarding the pure paraffin copper foam, for those foam characteristics, we'll see what the difference is. This is after 1 minute, after 2 minutes, 3 minutes. See how the PCM inside the tubes melt so quickly compared to the pure paraffin. After 5 minutes, 6 minutes, 7 minutes, and it almost melts almost completely after approximately 10 minutes compared to 31 minutes for the pure paraffin. So this is a summary for the process, for the comparison between the pure paraffin unit and the PCM metal foam based unit. So we see that's how fast has the PCM melts compared to the pure paraffin. Okay, so the main focus of this investigation is to see how the charging process develop. So selecting some points on the middle tube number 6, we can see that the closer the point to the tube wall, it melts faster. So if we see here, this is the at 0.1D and 0.9D, at 0.1D, which is the red one, while 0.9D. So closer than the tubes, the PCM experienced stronger heat fluxes and start to melt faster. Okay. The other thing, if we compare the different tubes, if we track the temperature at the center of the tubes, okay, for different tubes. So tube 2, tube 4, tube 6, 8, and 10. So the closer the tube to the upstream, it melts faster, while the tubes at the downstream area will see relatively slow charging process. For the foam characteristics, which is basically the porosity and the pore density, let's see how the pore density can affect our process. Increasing the pore density for a particular metal foam means increasing the interstitial heat transfer area available for heat exchange between the foam matrix and the PCM particles nearby. So with increasing the value of the pore density, the PCM inside the tubes melts faster, okay, due to the high heat transfer exchange between the solid matrix, which is the foam matrix, and the PCM saturated with. Looking at the impact of the porosity, we see that in reducing the porosity value acts similarly, but to a lower extent, okay? Because reducing the foam porosity means improving the overall thermal conductivity of the system. But this would be accompanied with some penalty, which is the further resistance to the flow inside the tube. So the buoyancy effect will be quite limited due to this resistance. Overall, so to summarize, with the increasing the pore density, the charging process is quite accelerated, and similar things with increasing the porosity, but for a different or for a lower level. Another parameter, design parameter we've inspected is the packing density. How much pipes do we have inside a certain volume? So the packing density is the number of tubes, okay, stacked in 1 meter width of the thermal energy storage unit. So looking here, while placing more tubes, inserting more tubes inside the unit, that means accelerating the flow and enhancing the heat transfer rate. Also, increasing the tubes means increasing the volume occupied by the PCMs. So that means increasing the storage capacity as well. However, with increasing the packing density, the pressure drop increases also. Lastly, let's see the porosity effect combined with the packing density. Similar thing we can notice, but to a less extent. However, the overall performance, which is the energy storage to the energy spent for running the system, this is the performance overall performance factor. We see that we increase the porosity for a certain level, then the performance starts to deteriorate. This is because the heat, the storage capacity goes down as the porosity reduce. That means as a lower volume has been occupied inside the tubes and lower storage density available. Thanks for listening, and you're welcome to place any question.